Hello and good evening. Today we would like to present about chlorine Graniteville disaster. But before we start, let me introduce you to my group members. First, me myself is Nur Hidayah, and the next one is Alexis, and the next one is Abdijani, and lastly we have Mahendra, and all of us are from Chemical Engineering Department. Moving on to the next part, which is introductions. I will briefly introduce our case study. Our case study is based on the Graniteville train crash, which occurred on January 6, 2005 in South Carolina. This accident caused a major chlorine gas release that affected the nearby community, making it a suitable case for studying toxic gas dispersions. The objective for this study are to model the downwind dispersions of chlorine using the RISKCURVES software and to evaluate how different atmospheric conditions influence the plume dispersion and the resulting public risk. The chemical involved is chlorine, which is stored as a compressed liquefied gas. When released, it forms a dense cloud gas that stays close to the ground instead of rising. Because chlorine is highly toxic when inhaled, exposure can cause severe respiratory damage and at high concentrations may result in fatalities. The incident occurred at approximately 2:39 a.m. on January 6, 2005, when Norfolk Southern freight train 192 was accidentally diverted onto an industrial siding and collided with a stationary freight train. The impact caused the derailment of several rail cars, including a tank car carrying on 90 tons of liquefied chlorine, which is punctured and released chlorine gas into the atmosphere. The release occurred near the Avondale Mills plant, which is located close to the Graniteville town center. As a result, the dense chlorine clouds spread toward the nearby residential and industrial areas, affecting thousands of people and leading to the evacuations of more than 5,400 residents. For our risk curve simulations, we use the actual release parameter, including a release durations of 258 seconds, a mass flow rate of 324.89 kg per second, and the corresponding temperature and pressure conditions. The image on the right compare the predicted dispersions of the chlorine plume under the daytime and nighttime atmospheric conditions, showing how weather conditions influence the extent of the affected area.
Next, I will be explaining the modeling assumptions and methodology used in the study. For the first one is the environmental assumptions. They were defined based on the Graniteville town center. The area was modeled as a suburban environment with regular large obstacles. The ambient temperature was set at 30 degrees Celsius during the day and 24 degrees Celsius during the night with relative humidity of 83%. Next are the three meteorological conditions that were considered to represent different atmospheric stability levels. These are F1 night, which has stable condition and low atmospheric mixing, B2 day with unstable condition and strong mixing, and C3 day representing moderate daytime mixing. This scenario will help evaluate how weather affects the dispersion model. So for the risk assessment, the base failure frequency was set to 1 times 10 power of -7 per year. The model also included separate day and night population distribution, allowing a more realistic estimation on the potential impact to the residents. The consequence modeling was performed using risk curve together with the effects software, following the standard slabs dispersion model for dense gas release. Finally, the figures at the bottom show the meteorological distribution used in the simulation and the effects map, which illustrates the 1% lethality zone around the Graniteville town center. This assumption will provide a reliable basis for the evaluation of consequences of accidental release.
Hello everyone, I'm Abdul Jani. Now I will proceed with our simulation outputs and hazard interpretation. For this study, we establish a toxic endpoint threshold of 205 and 6 mg per cubic meter at a downwind receiver distance of 500 meters. Looking at our result matrix, the impact of atmospheric conditions is immediately clear. Under the stable F1 night scenario, the population faced an extreme toxic dose, resulting in a 98.17% lethality rate. In contrast, daytime mixing offers some mitigation. The moderately unstable C3 day scenario shows an 89.57% lethality rate, while the highly convective B2 day scenario drops it to 77.12% due to enhanced vertical air mixing. Moving on to the next page, let's look at the downwind hazard footprint. The zone for a 1% lethality threshold extends to a maximum distance of 2,595 meters, heavily overlapping the town center. This variance highlights how atmospheric stability dictates public risk. During the F1 night, a lack of solar heating and low wind turbulence trap the dense chlorine gas close to the ground, preserving lethal concentration over long distances. However, during the B2 day, strong solar radiation generates thermal turbulence and rapid convective mixing. This actively dilutes the toxic cloud, significantly shortening the downwind hazard zone and reducing overall lethality. Thank you.
Okay, so this slide will show you the weather sensitivity matrix at 500 meters downwind, which compares the impact of different weather conditions on the chlorine dispersion. There are three types of scenarios that were analyzed, which is F1 night, B2 day, and C3 day. Each scenario will differ in atmospheric stability and wind speed. So for the first one is F1 night scenario, which represents a very stable atmosphere with lowest wind speed of 1.3 meters per second. But there is very little atmospheric mixing, so the toxic cloud will remain concentrated near the ground zero, resulting in highest lethality of 98.17%. In contrast, the B2 day scenario is highly unstable with stronger atmospheric mixing due to solar heating. This will disperse the gas more effectively, giving the lowest lethality of 77.12%. And the last one is C3 day scenario, which moderately unstable conditions and produces intermediate lethality of 89.57%. So overall, this result shows that the weather condition significantly reduce the influence of toxic gas dispersion, and stable night condition produce the most severe consequences, while unstable daytime condition reduce the hazard by enhancing the atmospheric mixing.
Moving to mitigation, our data proves that traditional outdoor evacuation is a fatal mistake. Near-field lethality exceeds 77% across all weather cases. We must shift our strategy from reactive fleeing to engineered defense in-depth containment. On the hardware side, we implemented automated high-pressure perimeter water curtains to actively dilute and dissolve the airborne chlorine cloud, paired with remote emergency isolation valves to stop the release at the source. On the administrative side, our primary directive is strict shelter in place. All occupied facilities within a 1.5 km radius must be equipped with toxic gas detectors that instantly interlock with HVAC dampers. The moment a leak registers, outside air intakes seal completely, transforming standard buildings into positive pressure survival havens. Ultimately, this challenge highlights a vital mindset shift for us as young engineers. Consequence modeling in effects show us the physical boundaries of a disaster, but true process safety requires integrating those footprints with failure frequencies and regional wind data inside risk curves. We discovered that safety is highly non-linear. A simple shift in the clock from day to night transforms a manageable release into an absolute catastrophe. Moving forward, our ultimate goal must be inherent safety instead of simply building expensive add-on barriers to handle 115,340 kilograms of liquefied gas. We must minimize baseline hazards by reducing stored inventory entirely. Where risk remains, the ALAP framework dictates that we ruthlessly implement every viable engineering safeguard to protect human life. That's all from me. Thank you.